Most RF engineers spend a lot of time thinking about conductors, antennas, and signals. But surprisingly, some of the most important RF design decisions involve materials that do not conduct electricity at all. These materials, called dielectrics, control how electromagnetic waves travel, store energy, and lose power inside RF systems. In the previous lesson, we learned that conductors behave differently at high frequencies because electromagnetic fields become increasingly important. However, conductors are only one half of every RF structure. Between conductors, around antennas, and inside transmission lines, there are usually insulating materials that interact strongly with electromagnetic fields. At first glance, these materials appear passive because they do not carry significant electrical current. Many beginners assume that RF signals travel only through copper traces or metal structures. In reality, a large portion of the electromagnetic energy often exists inside the surrounding insulating material. This raises an important question. If dielectrics do not conduct current, why do they have such a major impact on RF performance? Understanding this question is essential because dielectric materials influence almost every RF component and communication system. A dielectric is an insulating material that supports electric fields while allowing very little electrical current to flow. When exposed to an electric field, charges inside the material shift slightly, creating a phenomenon known as polarization. Unlike conductors, which allow free electrons to move easily, dielectrics primarily store energy within electric fields. This stored energy becomes part of the electromagnetic wave traveling through the structure. The most important dielectric property is permittivity. Permittivity describes how strongly a material responds to an electric field. Materials with different permittivities affect wave propagation differently, changing signal velocity, wavelength, impedance, capacitance, and field distribution throughout an RF system. Intuitively, a dielectric can be compared to a spring that stores energy when compressed. The spring does not create energy, but it temporarily stores and releases it. Similarly, a dielectric stores energy in the electric field established within the material. Physically, consider a microstrip transmission line on a printed circuit board. Many people imagine that the RF signal travels entirely through the copper trace. In reality, most of the electromagnetic field extends into the dielectric substrate beneath the trace. The substrate, therefore, becomes an active participant in signal propagation. Mathematically, dielectric permittivity influences the propagation velocity of electromagnetic waves. Higher permittivity generally means lower wave velocity and shorter wavelength. This is why the same transmission line geometry can exhibit completely different electrical behavior when constructed on different dielectric materials. Dielectrics are critical components in RF engineering because they influence nearly every practical RF structure. PCB substrates, coaxial cable insulation, microwave laminates, antenna radomes, capacitors, filters, and integrated circuit packages all depend on dielectric materials. For example, RF PCB designers carefully select substrate materials because dielectric properties determine characteristic impedance and signal propagation speed. Microwave engineers often choose low-loss substrates to reduce attenuation and improve system efficiency. Antenna designers may use dielectric loading techniques to reduce antenna size while maintaining desired performance. At the system level, dielectric selection affects communication range, signal integrity, insertion loss, bandwidth, phase stability, and overall RF system performance. Choosing the wrong dielectric material can significantly degrade a design even when every conductor dimension is correct. Dielectrics demonstrate that electromagnetic waves are influenced not only by conductors, but also by the materials surrounding them. In many RF systems, the dielectric environment plays an equally important role in determining how signals behave. A common misconception is that all insulating materials are essentially the same. In reality, RF engineers carefully compare dielectric constant, loss tangent, temperature stability, moisture sensitivity, and frequency response when selecting materials for high-performance applications. Although dielectrics help guide and store electromagnetic energy, they are not perfect. Real materials introduce losses that gradually convert signal energy into heat. In the next lesson, we will explore loss mechanisms and discover where RF power goes when it is not successfully delivered to the receiver. In this lesson, we learned that dielectrics are insulating materials that support electric fields and strongly influence electromagnetic wave propagation. We also saw how dielectric properties affect transmission lines, antennas, PCB substrates, microwave circuits, and overall RF system performance. In the next lesson, we will explore loss mechanisms and discover how RF energy is lost in conductors, dielectrics, and real-world communication environments. If you found this useful, like the video, subscribe, and follow for the next lesson.